So I'm now going to talk about using an observer, which is going to be a simulation of a real system to generate a state estimate, and how these things are very useful within the framework of state feedback control. If we remember, we've been previously talking a lot about output feedback control and why it's a good idea to have negative feedback. So in this simple system that we have up here, we have a forward path consisting of a controller, which is just basically something. It could be a PID controller, it could just be a scaling gain, so that we have an error going into the controller, being scaled, being modified, and generating an input command to the actual plant, which is a thing we're trying to control. This will then generate some kind of output. We then look at the output, could be using a sensor, it could just be directly, and we feed it back to the input so we can compare with what we want with what we've actually got. And basically doing this, we can actually try to drive the output, right, to be very much the same as what the input is. And this works much better than having just a feed-forward path, because it accounts for the fact that we might not know exactly, what the plant is, and it can also account for disturbances. However, we've also discussed the fact that it's actually much better to use the full state of the system for this feedback, as opposed to just using the output. Now, it could be that the output is the full state, but not generally. So if we've got a plant, it could be, let's say it was just a pendulum, and we've got a plant and we're just trying to balance it, not worry too much about the cart. We'd have, let's say, as in a very simple example, we'd have one of the state variables would be the angle of the pendulum, and the second might be its angular velocity. Now, it might be that we can only measure one of those things. We can, let's say we're using an encoder, we can only measure the angle, in which case we can't actually get the full state of the plant. And under those circumstances, it becomes very useful to be able to have some kind of system which can estimate the full state of the plant, so we can use that. So just to remind you why we want the full state of the plant, if we've got the full state and we can feed back the full state, then we can basically change, if you like, the eigenvalues of the control system to be not anything we want, but within reason we can change the eigenvalues to something more suitable than they would be in a feed-forward system. So we can make something that was unstable stable, for example. So that's why we want to be able to do this. But we need to find the gain in order to do that, clearly. We have to find the right feedback gain. So let's consider the situation now then. We've got the plant, and let's say there are some state variables we cannot actually see, right? Let's say we could only look at, if this was an inverted pendulum, we could only see, let's say, the angle, and we can't see the angular velocity of the pendulum. In this case, what we could do is we could say, well, okay, we can just see the angle coming out, but we want both state variables. So what we could do is we can actually have a model of the plant, right? We have a mathematical model of what the plant does. In fact, this is going to be a state space model, and it's generally going to be a state space linearized model of the plant. And what we do is we don't just feed the input to control the actual system that we want to control, we also feed the same input into our model. So we then simulate what the model actually does, and it can then simulate the full state of the plant. And we can then use this full state prediction in our feedback loop rather than actually using the actual plant, right? So we're using the actual prediction of state in our feedback loop rather than anything to do with what the plant's doing. And what this means is we now have this is a feed-forward model that we're using for state feedback control. So we can still basically put the poles of the controlled system within reason anywhere we want to. But there is a problem with this, okay? If the model of the plant isn't very good, then the prediction of the state won't be very accurate. There's another problem, and that is if the output for some reason is disturbed, so it could be that someone's changed, holding it or pushing it, or the wind's blowing or something, we don't actually know what's really happening with the output because we're not looking at it. So this system, for the reasons we need feedback, is not good. It doesn't deal with having the plant having uncertainty in our model of the plant, right? It doesn't compensate for the fact that we might be wrong with the model, and it doesn't compensate for the fact that the output might be disturbed. So what can we do? Well, what we can do is we can look at what we actually know about what the plant is doing. So the plant here will be generally generating some kind of output. It could be that this is then, if this is an inverted pendulum, what it's doing is we're measuring in the output angle, let's say, with the encoder, right? So, but we're not measuring the velocity, we're just measuring the output angle. And our forward model of the plant down here can also predict the full state. So one of the things it can predict is the output. So what we can do is we can say, how good is the forward model? And let's compare the forward model output with the actual output we've got. So what we do is we say, let's subtract our prediction from the actual output that we have, and basically we can generate this prediction error. This error tells us how good our forward model is. And if the error is 0, we know it's perfect. So in this system, basically what we need to do is now use this prediction error, if we can. So if this error is big, then we need to do something about the prediction. We need to improve it. So what we're going to do is we're going to use this prediction error to improve the prediction. And in a nutshell, what we need to do is we need to use this prediction error in order to drive the prediction to be the same as the output of the actual plant. So that's exactly what we do. Effectively, we build a little tiny, it's actually an output feedback controller that we're building into the system. We're saying we want the output of the forward model, right, to be the same as the output that we're actually getting. And what we do is we just have a feedback loop in the system that then basically, takes the output as the goal. It takes the prediction as being what we're generating by the model, and then using a gain, we have this feedback, this negative feedback loop to drive the model in order to generate the prediction that we actually see in the real world. So what we're doing is we're correcting the forward model, in this case, by using the real output. And this can generally reduce effects of inaccuracies in the forward model, and it can reduce effects of disturbance as well, and it can account for that as well. And that's just highlighting the system. Designing this control loop basically involves designing the gain again in the control loop, and we will generally want a gain that is as high as possible, so this is a very effective controller. But the important thing, once more, is that we make sure that when we design this, that this system, this predictor, is a stable system. There's no point in building something which goes unstable. Now, what I haven't mentioned so far is the fact that something nasty can happen with real systems, and that is the plant can sometimes have a delay in it. So, we do something and it takes a bit of time before the output actually appears. Now, that's a sort of a nightmare scenario for control engineering, because if you feed back an out-of-date output, you automatically get this phase shift, right, which is frequency dependent. So it's very easy for these systems to go unstable. So what you can do with the observer is actually say, well, actually what we can do is we'll make a model of the plant. When we use our state feedback here, we can make the model with no delay at all. And then we can get round the fact that this delay would normally cause all kinds of stability problems. So we can build a model which is acting straight away, and that's a very effective solution to building systems with delay. However, we still have to worry about the correction term, and we can only obviously get the output from the real system after a certain delay, because that's inherently built in. So if we want this correction term to kick in, we can only do that by then making sure that we compare the output with a delayed version of the prediction. So we have to have another delay in the output of the forward model here. but we're not using this bit for the control. We're just using our direct prediction for control. All we're using this correction for is just to improve the predictions. Okay. Let's now think about a formal analysis of this kind of simple feedback observer, and it's called a Leuenberger observer after its inventor. And we're going to start off in state space model terms, of course, by looking at what a state space model looks like again. And again, basically, this is just a signal flow depiction. In comes the input multiplied by the B. Obviously, then we estimate the x dot, and we can integrate it to get the full state x. And then we combine the input and the state estimate in order to get the output. I shan't go through that in too much detail because we've already covered that. And like I said before, you can directly type that into Simulink because it's a signal flow diagram, so you can actually virtually implement that directly within Simulink. And when we add state feedback control, so we feedback the full state, we can easily show that on this kind of signal flow graph. What we do now is we say we tap off the full state x, we multiply it by minus k, and don't forget this is a vector, this is a column vector, and this is a row vector. We multiply these together, and then that becomes the input u, and then often we have an input as well coming in here, a reference input which can be 0. If that's 0, then we're just trying to get the state effectively set to 0. So, in general, then the full state won't be available from a system. So what we can do is actually estimate it, like we just said. And it could be that you can't get the full state simply because you just haven't got access to things. Like I said, you might have only access to the position and you want the velocity as well. Could be loads of other things in other scenarios. In chemical plants, there's massive numbers of things you can't measure. So what do we do? Well, we need to be able to estimate now, like I said before. So what we're going to do is we're going to build. Let's start off with a feed-forward estimate of the state. Again, now we're writing things absolutely in terms of state space models to get very concrete in what the actual design is all about. So we've got our state space model. In fact, this is a state space model of it's also kind of a simulation, but we're just using that as an example here. Here's a state space model, and now we're going to build a simulation of this state space model. In practice, this would be actually a real system, and you just have the input going into this block, and you just have an output. But just to make life easier to understand, let's imagine that this is also, in this case, a simulation. We can build a model of this state space model as well, quite easily, by basically replicating most of it, right? So we replicate it up to the point that we generate the state estimate. So here we're generating the state estimate x, and here now we're just going to estimate the state estimate x hat. Right, so this is actually what the observer, the forward model, is going to be doing. It's estimating what the status of the system is. And now what we're going to do is we're going to use the estimated state from our observer in order to do state feedback control. So we're calling it x hat because x hat is now going to be the estimate of the state of the system as opposed to what the actual state of the system is. So we have the corresponding slight change in the state space equations. We now say it's x hat dot equals ax hat plus bu. So let's analyze this feed forward system. We start off with the equation x hat dot equals ax plus bu, where x hat is now the open loop estimate. And we want to know what the actual error is between this open loop estimator and the actual system. So all we have to do is we say, well, the state error is going to be x, which is the actual state, but we don't know what it is at the moment, but x is the actual state. X hat is the estimated state, so x minus x hat is going to be the state error. We're going to call that xe tilde, right? if we differentiate both sides of that equation, we can say that we've got the differential of the error, of the state error, equals the real state differential take away the predicted state differential. But we can now substitute in what these systems are actually doing in terms of their state space models. We know that x dot, this is for the real the actual system first of all, x dot equals ax plus bu. So we can substitute that in, and we can also substitute in the equation for x hat dot. So this is our predicted state. We can substitute both of those into the equation, and what we get is the differential of the error is now ax plus bu take away ax hat minus bu. Right, so it's one might take away the other. So we can just simplify that, and we end up with x hat dot equals ax minus ax hat. So let's factorize that out. As we can see, we've now got the differential of the error is ax minus x hat. But we know that actually that x minus x hat is actually the state error that we had before. So we end up with the equation x. Well, basically what it says the differential of the state error is a times the state error, right? So that's basically a very similar result that we get from a state space model. It's saying that the differential of the error is equal to a times the error state. And because we know for systems of that form, in this case, we know x dot equals ax plus bu. In this case, there's no bu, but we know that these systems are stable provided the eigenvalues of the A matrix have negative real parts, right? So what we need to do is we need to calculate. Well, we need to consider what's going to happen. What do we think about we need for an A? So we need the equation such that the determinant of A minus lambda I equals 0, just like we always do, right? So basically then all we're saying is we can consider this error expression as being very much just like a standard state space model, and we want the error dynamics to be stable, right? We want the error, in fact, we want the errors to die away with time. So we want the eigenvalues of A to have negative real parts. So what that's basically saying is if we build a system, right, that we want to control, and we want to build a simulation of it, and we want to use a feed-forward observer, we can only do a feed-forward observer if the system we're actually trying to model is actually stable already, right? If it's not stable already, we can't do it because it means that we're violating this condition. It means the error will never die away. So that means, for example, in case of a pendulum where we're trying to analyze a system which is actually unstable and use state feedback control to actually stabilize it, it means we can't just use a feed-forward model of the system in order to estimate the state. This is where another reason that we seem to now land up with needing to use a closed-loop observer, which we talked about in terms of using actually the prediction error as well in order to improve performance. So here is the model then of the closed-loop version of an observer modeling a system. So again, we're just considering the system again as a state space model. Again, like I said, in the real world, this block up here would be a real system, so we can't poke around inside it, but we can put the input in and we can get the output out. But now what we're doing is basically we're saying, well, we've got all the feed forward part that we had before, right? All of this bit round here, this bit round here is the same as it was before. It's just basically estimating x hat. But the difference now is we're now looking at the output it produces here, right? We're looking at the output prediction and notice the minus C there, so that still is actually a negative. And we're comparing what the output from this real system is, and we're taking away our prediction to get this prediction error. And now we're scaling this prediction error, and we're using that to feed back into the system here in order to actually try to minimize the prediction error. And then just in the same way, we're using the x-hat for state feedback control. So we've added this little controller loop here in order to make sure that the system actually does a better job predicting than it would have done otherwise. And another nice aspect of this is the fact that if this system, right, if the feed-forward system was actually unstable, this can actually stabilize it as well. Okay. And using this particular approach, where we've got this structure, and designing the L here, I'm using L because it's a Lüneburger observer, designing it on the basis of considerations of stability is what Lüneburger observers do. Now, you'll probably come across things called Kalman filters as well at some stage, and Kalman filters effectively use the same structure, but they have a much more sophisticated way of estimating what the gain is. And they actually look at statistical considerations, and they propagate uncertainty as well in calculating what the gain should be. We're just going to go for a very simple, if you like, pole placement approach for designing this, because that captures the essence of what an observer is. Right. So this is the state space model that we're trying to actually simulate, and here is the open loop part down here, and here is the corrective part that gives us our closed loop observer. Okay. So now let's look at the equation that we're going to get for x hat dot. If you remember, x hat is our predicted state. X hat dot is going to be its differential. If we look at what we've got here, we just go through them. It's going to be a x hat. So it's going to be leading into this particular point here. It's going to be a times x hat plus input here is u, so it's going to be u times b, so a hat hat bu, then plus, and now we've got this extra feedback path coming in here, plus y, take away c times x hat, that is multiplied by L, right? So we're adding this bit on here as well, right? And this is the bit which is going to, first of all, correct our state estimate. And there's the state estimate. That's the system, the open loop term, and that is our output correction term. Okay. So let's think about how do we choose L in this system? Again, what we can start looking at is analysing the error of the system, and again, we want the error to die away, right? We want the system to be stable. We want the system error to die away as time progresses. So again, what we do is we calculate the error in the system. So the error of the system is a state error x minus x hat. We can differentiate that, so it's the differential of the state error equals x. The differential of the state, take away the differential of the predicted state. We substitute in the state space equations again, but this time we've got this other term in here as well for the Lüneburger correction. So we put in, the first bit is the prediction of what we get for x dot. This is the then prediction of what we get from x hat dot. We cancel out, right, that's just putting those in, making it completely obvious. And we've also got y equals cx for the real system, right? So we can put that in, right? So that's if that's the state of the real system, then c is the output vector, so y is cx. We can put that in there as well, and we end up with an equation a x minus x hat minus lc x minus x hat, which we can then simplify a bit more, and we end up with the equation for the error differential. So error differential equals a minus lc multiplied by the error. Okay. So what this is telling us, if we want, now we want this to be stable as well. Again, we want the state error to disappear as time goes to infinity. Hopefully a bit quicker than that, but that's the mathematical way of looking at it. So what this is saying, now we can compare that again with the kind of equation we had before for the state space model, and we know before it's the A matrix that we care about, but now we have a modified version, and we have now an A minus LC matrix. So what we need now is that the eigenvalues of A minus LC have negative real parts. And if that is the case, then we're going to have a system where the error decays away and it'll be stable. So in actual fact, designing the Lüneburger observer comes down to designing the gain L, right, in this case, and it's very, very similar to designing the K in a state feedback controller, and we can use exactly the same methods to actually design this as we design state feedback controllers. So that's basically it. The only thing is we use different matrices. We care now about A and C in order to get L rather than A and B in order to get K. So I said a couple of times, when we're looking at the real system, obviously we don't have a state space model at the top. We were just putting that in order to so we can actually compare and analyze and come up with the equations that we need for deriving what the actual gain and what the properties of the system got to be. This is more like a real system would be like, right? So we've got our reference coming in, which could be 0 if we want everything, if you want all the states to be 0 when it's fully controlled. We've got our input going into the plant, right? So this could be, if this was the inverted pendulum, that would be like driving the stepper motor. It gets an output, which could be just the angle from the pendulum, and we can't see inside it. We can't see any states. We don't know what's going on. All we know is, we turn on the motor and it moves, and something happens, and we measure the angle of the pendulum, and everything else is hidden. So that's much more realistic view of what a real system looks like. You can't see inside it. It's like a box, a black box, that we can now still tap off the controller, right? We still tap off the control, put it through our Lüneburger observer, correct the output from the output that we do actually have, and generate our state estimate x hat, and use that for full state feedback control. Right, that's the important thing. So to summarize, generally we don't have the full state of a system, right? And we want to estimate it using an observer. And whenever possible, we should also use the actual output of the system in order to improve our state estimate. So let's just now compare closed-loop state feedback control with designing the Lüneburger observer system. In a closed-loop state feedback control system, we know that we modify U equals minus Kx, so that leads to the updated state equation x dot equals A minus BKx, and it modifies the output equation to C minus DK times x. Stability now is going to be determined by the location of the real part of these eigenvalues of A minus BK. And we want the eigenvalues of A minus BK to have negative real values, right? So basically the system will end up going to 0. It's not going to build up and up and up. And we can design this using the place command, right? We can design this using pole placement. We give it A, we give it B, we tell it where the poles should be, and we asked it for the gain, right? We can do that. You can do it by hand as well, of course, as you will be doing in exams. In the Lüneburger observer, we got an error dynamic equation. So the differential of the error is given by A minus LC times the error, right? And in order for this to be stable, this time we need to consider the eigenvalues of A minus LC, in particular the real part, and we need to choose L so that we have negative real eigenvalues, right? exactly the same way. So basically the system is stable, so the error will decay away over time. We don't want it to be building up. And you can use the place command to design this as well. Again, you just give it the poles that you want. This time we need to use the A and the C in order to get this to work. And just a little tip for MATLAB, the way it wants the vectors to be organized, basically, I think it wants a row vector for C, and obviously it comes, it wants a column vector, but you obviously you end up, you have got a row vector, so you need to transpose it with a little dash at the end in order to get the thing to work. So the idea then with this pole placement is to choose L, so A minus LC has negative eigenvalues.